Here are the solutions on the last page of the review problems. The first problem here is similar to the one we just did, where we're talking about taking something that we have verified in a lot of settings for various numerical values of p, but then just trying to make an argument once and for all in terms of the parameter p for what's going on. So we know the integral test tells us that a series converges if the corresponding improper integral converges. So, oops. So in each case, what we're trying to verify is, do we understand what's happening with this continuous integration problem? So there are a couple of things that happen with this. Don't forget that the idea here, when we're doing an improper integral, is that we're going to take the limit as n goes to infinity of the answer to the definite integral problem. So that's the first thing. And actually, I'll go ahead and write my integrand using x to the minus p, because I know that's going to be my how I want it written to be able to use my power rule. So that integral, well, one thing to put an asterisk next to is that if that power p is 1, then we're not using the power rule. If the power is 1, then we'd be talking about the antiderivative being the natural logarithm. So we'll put an asterisk there to remind ourselves that we're assuming here that p is not 1 to be able to do this step. So, but p equals 1 is just one very small case. So this will be true every other time that what's inside the integral will be the power rule. So remember, the power rule is that the power goes up by 1 and we multiply by the reciprocal of that new power. And that gets evaluated from 1 to n. And so I'll have the limit as n goes to infinity of minus 1 over p plus 1. Well, let me just write that. Hang on. So when I plug the numbers in, putting n in for x is going to give me 1. Instead of negative p plus 1, I'm going to write that 1 minus p. That's hard for me to get the parentheses straight on that. And I'll have n to the 1 minus p. And then minus, plugging in 1 for x, I'll have minus 1 over 1 minus p. So that's what it'll look like. The p is constant, so that 1 over 1 minus p term is going to be the same no matter what. And so the only question is, what's happening here as n goes to infinity? Well, it depends on the power. If that's n to a negative power, then that thing is going to go to 0. So that's going to go to 0 if the power is negative. And that thing's going to go to infinity if the power on it is, well, I guess I should say greater than 0. So if you're raising n to a positive number power, then as n goes to infinity, that power goes to infinity. And if you're raising n to a negative number power, then the power goes to 0 as n goes to infinity. And so that's where we're getting the two cases for convergence. 1 minus p being less than 0 is the same thing as saying p is greater than 1. And 1 minus p being less than 0 is the same thing as saying p is less than 1. So we have divergence of the original series. So we have convergence if p is greater than 1, and we have divergence if p is less than 1. So that whole argument tells us that. There's one term that's left out, and that's what happens if p is equal to 1, and that was the subject of our little footnote there. We can do the analysis of p equals 1, but the integral will be a different integral. So that's why it's not included in the analysis of, that we've done so far. So it really is just a matter of going back and looking at the series 1 over k to the first and comparing that to the integral of 1 over x. And if you do that analysis for the integral test, you'll find that that also diverges. So when p equals 1, we also get a divergent series, but for a different reason. We have to actually do the integral and we get a different number. So that means that the divergence case here should be not only if p is less than 1, but also if p is less than or equal to 1. So that's exactly the fact that we stated for p-series, and we can see here how it works, how it comes from the corresponding fact for improper integrals. Number 7 is just to remind you about the geometric series formula. There are only a few things in this course that are formulas like that are very exact and come up in other settings in math. So I want to just remind you of that. But it really is just using the formula. The first term here is just what I get when I put the first value of k in. The k for this series starts with 2. So when I put 2 in for k, I have negative 1 squared times 2 cubed over 4 squared, which is 1/2. The ratio between successive terms here is negative 1/2. If you're not sure about that, just figure out the first several terms and look at the ratios. Or you can do the ratio test sort of formally and see that the r really is negative 1/2. And so therefore, the formula that we get is first term times 1 over 1 minus the common ratio, whatever that ends up being. So it's just a formula using the first term and the common ratio. But it is a good formula to remember. And then the last problem that we have here is pointing out something that's interesting about midpoint and trapezoid rules. I had said in one of the videos that what's interesting about them is that when one of them is underestimating, usually the other one's overestimating. That happens for the most part. And so what that means is that some kind of average of the two ought to be closer to being right. But there is a kind of a scientific way to do an average of the two, and that is to do a weighted average where we use 1/3 of the trapezoid rule's prediction and 2/3 of the midpoint rule's prediction. And that's motivated by the fact that the midpoint rule, if you remember the error formula we talked about, the error formula for the midpoint rule says that the error typically is going to be about half the error you get for the trapezoid rule. So in other words, the midpoint rule is closer to the right answer and kind of estimates in the other direction. So doing a weighted average where we put more stock in the midpoint rule and less stock in the trapezoid rule not only makes intuitive sense, but if we were to follow that through, it actually gets the answer very, very close. So close, in fact, that it's implemented in a lot of computer systems to do estimates of these sorts of things. And it even has a name. It's called Simpson's rule. So what this problem is asking you to do is just to do the midpoint and trapezoid estimates using just one subinterval in each case, and then forming the weighted average to see that it actually gets the answer exactly right. And that'll be true for any cubic polynomial. The weighted average of the two, of trapezoids and midpoints, gets the answer exactly right if you were to apply it to a cubic polynomial. So this is what it would look like. The midpoint rule, we're going integral from 0 to 2. So we're talking about this shaded region. The midpoint rule would say find the midpoint of the subinterval. So that's right there. We're just using one interval. And then draw a rectangle at that height. So there's one midpoint rectangle. So the area of that one midpoint rectangle is the width, which is 2, times the height, which is f of 1, which is 6. So this is coming from f of 1. So that would be a rectangle of area 12. So 12 is how much area is in that that rectangle. And you can see that it's probably too big overall. It's got a lot of extra on the left side and not very much left over on the right side. So probably that estimate's too larger than it's supposed to be. But let's do the trapezoid. So same idea. We're only going to draw one of them. So one trapezoid would be to take the two heights. Here's a height there and a height there. Draw a straight line between them. the trapezoid rule is telling me the area of that trapezoid as an estimate, we can definitely tell that's too small. And you can also tell it's pretty much worse than the midpoint rule. And that's what our error bounds tell us. But the trapezoid rule would be the width of the trapezoid times the average height. So I'll have the average of the left-hand height, that's f of 0, and the right-hand height, which is f of 2. So that's 2 times a half, so that'll cancel. And f of 0 is 1, and f of 2, what is f of 2? 5. 1 plus 12 minus 8, 5. Yeah. So the trapezoid would say 6. Now we believe the midpoint was closer, but the theory tells us that the real answer is actually somewhere in between, and we can find the answer by just doing the weighted average of the two. So I'm going to do a weighted average where I put twice as much stock in the midpoint estimate as I do in the trapezoid estimate. So that's 1/3 of 6 plus 2/3 of 12. So that's 2 plus 8, which is 10. So, and I won't do it here, but the point is that if you were to do this integral exactly using the fundamental theorem of calculus, you should also end up with 10.